So, good morning to one and all. Today we have discussed the applications and analysis of beam using the influence line diagram. Actually, influence line diagram is related with, or we can say that it is the another method to find out the reaction at support, shear force and bending moment at given section. At the same time, we can find out the location of load for maximum bending moment or maximum shear force or maximum reactions. This influence line diagram is used not only for the determinate structure, it is also for the indeterminate structure. That means the as well be continuous beam, it is applicable, as well as for the truss we can use the ILD. So these are the few application to determine the support reaction at support, to determine the shear force at given section, to determine bending moment at given section. At the same time, as I told you, to determine the location of the load. That means the position of the load where we get the maximum shear force or maximum bending moment for the given section. Now the question is, generally the question may be asked like this: sketch the ILD, that is the draw the ILD for the shear force, bending moment or support reaction for a simply supported beam at a distance of A meter from support A and B meter from support B, and consider the total span of the beam is say L meter. So in that case, here this is the diagram. The diagram is very simple. When we draw the ILD for the support reaction, we can see that one increment is provided at A and 0 at B, and then you can draw the triangle. Similarly, when we draw the ILD for the reaction at support B, we can apply the one increment at B and 0 at A, and then draw the triangle. Okay. And when we find out the reaction, that is equal to summation of, say, point load is there, point load and multiplied by vertical increment of the ILD. That means the load below the vertical increment. And if there is a UDL, if UDL is there, in that case, we can take the area of the ILD multiplied by UDL. That gives the support reaction. The formula for the shear force, bending moment or support reaction is same. Okay. Now this is the ILD for the shear force at C. This is the joint C. We can say that this is the point where we require the shear force and the bending moment. So at point A, we can draw the vertical line, or we can draw the first the ILD for the, this is the, we can say that the one, that is the ILD for RA, and similarly below the reference line we can draw the ILD for RB like this. This is the ILD for RB with -1 increment. Okay, and here this is the section where we require the shear force. At this point, draw the vertical line which cut this, dark this line. That means this line. This is the vertical line and dark this line. That gives the sorry, ILD for the shear force. Left toward the right, toward the section, it is negative, and upward this is positive. Okay, so this is the ILD for the shear force at C. Similarly, for the ILD for the bending moment, at A it is 0, at B, that means both support, it is 0, and where we require the bending moment at C, we can take, this is A distance, this is B distance, and L is the A plus B. That's why A into B divided by L, that gives the vertical increment or height of this triangle. That is the ILD for the bending moment. Now this is the ILD for bending moment and ILD for the shear force. Okay. So If there is a cantilever beam, sometimes the beam may be cantilever. In that case, you can extend this line, and at the same time, you can extend this slope in this direction. Here it is observed that this is positive, this is below the line, that's why this is negative. Similarly, for bending moment also, you can extend this line up to this line and extend this slope below the line, and we get the negative bending moment. Okay. In this way, if you extend if there is a overhang on both the side, you can extend this line, extend the slope of the shear force diagram. This is again positive. This is the shear ILD for the shear force if overhang on both the sides. Similarly, for the bending moment also, you can extend the overhang portion and then extend the slope below this, and we get the bending moment ILD for the bending moment, which is negative. Below the reference line negative, above the reference line it is positive. So in this way, we can sketch the ILD for the shear force, ILD for the support reaction, ILD for the bending moment. This is related with, we can say that the, of course, these are not the bending moment diagram or shear force diagram. These are the influence line diagram. Remember. And when we find out the shear force or bending moment, that is equal to load multiplied by vertical increment in case of the point load is there. If there is a UDL, then we can take the area of that ILD under the load. Okay. So in this way, we can find out the support reaction, shear force and bending moment using the concept of the ILD. Okay. So let us start the problem. The problem is, simple problem is given. Apply the concept of ILD, that is the Bloom taxonomy level is 3. Determine the reaction at support A and B for the given beam loaded and supported as shown in figure. The problem is very simple. There is a UDL. There is a UDL 10 kilonewton and point load 20 kilonewton for the simply supported beam. Generally, using the equilibrium equation, we can apply the summation fx is equal to 0, summation fy is equal to 0, and moment about any point is equal to 0, we get the support reaction. But using the ILD, this is the very simple concept and simple to understand. For ILD, we can say that just by drawing the one increment at support A to find out the, or to sketch the ILD for RA and 0 at B, and then draw the triangle. Okay. And this line indicate the, we can say that the ILD for RA and RB. Here it is observed that the load 10 kilonewton acting over this trapezium. That's why we can take the area of this trapezium. So here we have considered this area. This is the load or area of the ILD under UDL, that is the 10 kilonewton per meter. And for 20 kilonewton, this is the vertical intercept. Again, we know that this is the one triangle, this is another triangle, and this is the big triangle. But the slope is same, slope is constant. That means the theta is constant. That's why we can take the ratio 1 divided by total distance. Total distance is 9. So 1 by 9 is equal to, this distance is say y1. So y1 divided by 6 meter. So we get y1 is equal to 6 by 9. Similarly, if we have considered this is y2, so this y2 divided by 3. Therefore, we get the 3 divided by 9. This is 3 meter, total is 9 meter. That means it is just the ratio of the length. Small, this height is 3 and total height is 9. So 3 by 9. This is 6 meter and total span is equal to 9 meter. That's why 6 by 9. And this 1, that is 9 meter divided by 9. That's why it is 1. Okay. Similarly, for the ILD for RB, again for B support we have put 1, and for A support we have put the 0. In this way we get the ILD for the RB. Here also we have considered um, distance. This height is this length is equal to 3 meter, and total length of the big triangle is 9 meter. That means total span is 9 meter. That's why this is 3 by 9, this is 6 by 9, because this distance is 6 and total distance is 9, and this is 9 by 9, that is 1. This is the ILD for R. And repeat the same procedure. This load 20 kilonewton per meter multiplied by this area, that means the area of the triangle. For RA, it is area of trapezium. For RB, area of the triangle. Plus, this load is given 10 kilonewton over the 6 by 9. So, in this way, we can find out the RA and RB using the concept of ILD. So, RA is equal to load multiplied by vertical intercept of ILD in case of the point load. And in case of UDL, we have considered the area. Therefore, the area under the ILD, that is half, that is the vertical height of the two parallel sides, 1 plus 6 by 9 multiplied by distance between the two parallel sides. See, this is this one. These are the two parallel sides of the trapezium. So half 1 plus 6 by 9 multiplied by distance between the two parallel sides, that is 3 meter. So we get the this load multiplied by this area, and this load multiplied by this height. So we get the RA is equal to 10 kilonewton is the UDL into half 1 plus 6 by 9 into 3 plus 20 is the point load into 3 by 9. We get 31.67 is the reaction at support A. Just in the one sentence we get the value of RA. Similarly for RB, repeat the same procedure. Area of triangle is there, that is half base is equal to 3 meter and height is 3 by 9. So half 3 by 9 into 3 into 10 kilonewton UDL plus 20 into 6 by 9. This is 6 by 9, that is 18.33. In this way, we can find out the support reaction. Another problem is related with the simply supported beam with overhang on the left side. Calculate the shear force and bending moment at a section 2 meter from the support A, and applying the concept of ILD. From support A, we can find out the shear force and bending moment. Okay. So for the this is the ILD for RA, but it is not necessary to draw the ILD for RA or RB, because in the question only shear force and bending moment is required. That's why no need to draw the shear force ILD for the RA and ILD for the RB. This is just for your reference. Okay. So, okay. This is the ILD influence line diagram for the shear force. At support A, it is 0. At support B, we have taken the total span is 4 meter. Remember, distance between the two support is 4 meter, right? This one. And we can take in the section at a distance of 2 meter from the support A. That's why this is at the center. So A is equal to 2 meter, B is also equal to 2 meter. Okay, and this overhang portion is 1 meter. Okay, so for 2 meter, left to right, it is minus, negative. So 2 divided by 4, it is 0.5. So 0 to 0.5 is the first triangle with minus sign. Then this is 0.5, and then straight line where we take the section for the shear force, and B is also equal to 2 meter. So 2 divided by 4, again 0.5. This total height is 1, 0.5 plus 0.5. Okay, then at support B, it is 0, and then extend this slope up to the 1 meter span. And that's why, as this is we can see that similarity of triangle, because slope is same. This is 0.5 divided by 2, that's why this is say y divided by 1, that's why it is 0.25 minus. Okay, and in this way we can find out the shear force at a distance of 2 meter. So UDL, total UDL is there. So first we will have considered the minus, and second we have considered the plus. So half, this is 2 meter multiplied by 0.5, that is the half 2 into 0.5, that is the area of this triangle, multiplied by UDL intensity 9 kilonewton. Okay, and for this minus, so minus again, this is also 2 meter 0.5, and intensity is same because the UDL is throughout the span 4 meter. That's why it is this is totally 0. And minus 12 is the point load into this distance, that is minus 12 into 0.25. That's why the shear force at 2 meter distance, it is minus 3. Okay. Similarly, we can draw the ILD for the bending moment. Repeat the same procedure. We have taken the bending moment at 2 meter from the support A. That's why A is equal to 2, B is equal to 2, and the total span is 4 meter. So 2 into 2, 4 divided by 4, and that's why the total height is 1. This is 1. Okay, so this is 2 meter, 2 meter. We can draw the ILD for the bending moment. This portion is overhang. That's why this slope is extended below the reference line up to 1 meter. And as this is 1 meter over 2 meter, similarity of triangle, this is 1 meter. That's why this will be 0.5 meter. This is the ILD for the bending moment. Repeat the same procedure. Area of this, total area of this triangle multiplied by 9 kilonewton per meter, that gives the bending moment for the span, and for point load, which is 12 kilonewton into 0.5 with minus sign. So we get the net bending moment at a distance of 2 meter, that is 12 kilonewton meter. Okay, this is the application of the ILD. Okay. Third problem is also similar. Apply the concept of ILD. Determine the reaction at support A and B for a given beam loaded and supported at shown in figure. Here we can find out the uh, reaction at support A, reaction at support B using the concept of ILD. So first of all, we can draw the ILD for RA, ILD for RB, and then this load multiplied by area under ILD, this load multiplied by vertical intercept of ILD, and this load multiplied by vertical intercept of ILD, that gives the value of RA. And same procedure is applied to find out the RB. Okay. Okay, all these problems are on the same line, so you can easily solve. And in the beginning, I have already discussed how to draw the ILD for support reaction, shear force, and bending moment at the given section. This is the overhang portion. ILD for RA, RB, you can take the 1 and 0, draw the ILD for in between A and B, and then extend if the overhang is on the left side or right side. Okay, and draw the ILD. So this is the sketch. You can see this sketch. This is 1, this is at support A, this is support B, this is 0, and you can extend this line beyond this and beyond this. This is below, that's why minus, this is above, that's why plus. And this is C, this distance is C, total distance is L, that's why L plus C. This is the total divided by L. So C plus L divided by L. This is 1, as it is greater than the 1. And this distance is D, total is L, that's why it is D divided by L. This is the ILD for the reaction at support A. Similarly, for reaction at support B, repeat the same procedure. We have considered the same procedure. Here also 1 kilonewton at RB and 0, and then extend the slope beyond the support A and beyond the support B. This is also L plus D divided by L because it is bigger one, and this is C divided by L, and we can find out the reactions. Similarly, for the shear force, support A, it is 0, then A distance divided by L, B distance divided by L, it is positive, this is negative. Okay, and extend this up to point B, and beyond point B there is an overhang, that's why extend the slope, which is below, that's why minus, and here also it is above, that's why this is plus. This is not minus, this is plus. Okay, this is the ILD for the shear force. Similarly, ILD for the bending moment, repeat the same procedure. This is the support A, this is the support B. ILD increment at support A and B is 0, and at section it is AB divided by L, small a, it is not capital A, small a into B divided by L, and extend the slope if there is a overhang portion from A as well as from the B. So this is about the ILD for bending moment, right? So you can easily draw the ILD for bending moment and shear. On the same line, you can draw the ILD for shear force, ILD for bending moment, and ILD for the so, shear force bending moment. Okay. So up to this, we have considered the only loads are fixed. Next lecture, we have discussed the if the loads are moving. Thank you. Thank you.